Continuing on with where we left off before, we were talking about the polar form of a complex number. And the polar form is incredibly helpful. It's going to allow us to do some amazing things. We're going to see in the video in a few minutes how we can really take advantage of that. But again, what we were holding on to, and like I said, this is a topic that shows up a lot in calculus too as we talk about polars, is that the link between the rectangular system, and of course when we talk about just plotting points in an xy plane with an x coordinate and a y coordinate, that's called a rectangular form. That has its benefits, and we can use them in wonderful ways. But polar form is going to be a wonderful shortcut that we can use as well. We're going to continue to talk about that. But I'd like to do an example with you right now that's actually an old contest question. And very quickly, let's just take a look at this type of a problem. 5 minus 10i is written in polar form. So it's going to be written as r cosine of theta plus I sine of theta. We could call this cis notation as well. R is greater than 0 here. They want us to find what r in this situation is times the tangent of theta would equal. So this is a real contest question going back a number of years ago. Let's very quickly just take a look at what this would look like on an Argand diagram. We'd go 5 steps to the right on the real axis, go down 10 steps, and of course we could find this distance d, which by the way we can also now call r. And in fact, because we have that r, that might be more suitable. I think we can definitely take advantage of that. Principle of the reduced triangle from geometry says that we could divide out a 5. Take a look at this. This is a real slick way to do that. Here's 2 squared plus 1 squared. That's 4 plus 1 is a 5. So w is actually going to be equal to the square root of 5, we would see. Now, understand that what we really have going on here is another triangle. This is the reduced triangle. R would have to be double that, 2 times r radical 5, because that smaller triangle, 5 times that. It's 5 times smaller. We divided 5 from all the sides. So sorry. So r would equal 5 root 5. Now you could have used the Pythagorean theorem here as well, and you'd get that to be true. But as we very quickly look for theta, we could say, well, theta we are going to be addressing in just a moment, but we really need to find out what the tangent of theta is. We don't have to write this out in cis notation. We certainly could, but it's much easier for us to just say, look, r we already know is 5 radical 5. What is the tangent? Well, the tangent of an angle, and remember this is a 4th quadrant angle. By the way, that's going to be very, very particular in just a moment. But tangent is always the opposite over adjacent. So the tangent of this reference angle that we see is the opposite side all over the adjacent side. That would be 2. However, theta is really going into the 4th quadrant. We remember all students take calculus. Only cosine would be positive in that quadrant. Of course, the tangent of theta is really going to be negative 2. Really, our 10 here, of course, we saw was negative anyway. So this is 5 root 5 times negative 2. Final answer would be negative 10 times the square root of 5. Okay, so There are some real powerful tools, though, that we can have working with polars. What I'd like for us to very quickly take a look at is this. If Z1, the first complex number, is R1, and we'll write this out in cis notation, and we'll say this is cosine of theta 1 plus I sine of theta 1. And a second complex number is given to us. We could say Z sub 2. Well, we'd have a different R value, of course. We could call it R sub 2. And over here is the cosine of theta 2 plus I sine of theta 2. Well, in polar form, in this cis notation, we have something that's just amazing. Look, if I were to multiply two complex numbers together, guess what we're going to do? We're going to take R1 times R2, but then amazingly, we're just going to add these angles together. We're going to have a new cis form, and it's just going to be a wonderful shortcut with us being able to write out the multiplication very, very, very quickly. The division, I think we can appreciate even more. If I were to take Z1 divided by Z2, well, we'd have R1 divided by R2. You might guess we're going to subtract our angles. We are. This is just a delightful shortcut. Division, usually you could see we'd have some work to do with conjugates. And this is a wonderful way that we can work this out. But perhaps one of the most powerful applications is when we very simply take a complex number and raise it to the nth power. Now, if you think about it, raising a complex number to a power really means multiplying that complex number to itself. So we're really going to go back to this first rule of multiplication. It's just that our R1 and R2 are going to be the same value, of course. And we'd be doing this however many times. So we would just say it's R1 to the nth power. Now notice that we always would add our thetas together. Well, if you were to add theta to itself n times, well, repeated addition is really just multiplication. So look at this. This is just flat out amazing. It's a wonderful shortcut to raise complex numbers to a power. And I'd like to immediately give you an example to let you know how to do this. Let's just say that we have z is equal to 1 plus I. And we'd like to write z to the third in x plus yi form, or iy form. Now, what I want to point out is that it's not excessively difficult to multiply 1 plus I to itself 3 times. We certainly can do that. The real benefit, I think, is as we're raising our complex number to even higher powers, maybe to the 10th power or beyond, and all of a sudden you'd realize, oh my goodness, I don't want to algebraically FOIL that out. So what we could do real quickly is make an Argonne diagram. We could say, look, I'm going to go one step to the right. I have a 1 out in front of my eye. Hopefully you can see very quickly this is the 45, 45, 90 right triangle. That means this angle here is pi over 4. And of course my radius would be radical 2. Writing this out in cis form, we'd have radical 2, and then this is the cosine of pi over 4 plus I sine of pi over 4. So at this point, we could say, well, let's see, what if I wanted to raise this to the third power? Well, that means take radical 2, raise it to the third power, but then multiply 3 to the angle inside. Oh my goodness, this is actually quite doable. It's going to be way less work than having to algebraically multiply everything out. Now, radical 2 times itself 3 times, well, I'll just jot that down off to the side. 2 radical 2's together multiply to a 2. So this just becomes 2 radical 2. Cosine of 3 pi over 4, well, 3 pi over 4 on the unit circle was over here in the second quadrant. Cosine would be negative, so this would be negative root 2 over 2, or as I like to write it, negative 1 over root 2. Sine, however, is positive, so this would become 1 over positive root 2. Finishing this up, well, you just have to distribute. I think you can see why I like to write root 2 down below. You can see when you distribute, these radical 2's are going to cancel out. You'll have negative 2 plus, over here is 2i. Of course, you'd get the same answer working it out the other way, but the real benefit where we can truly begin to appreciate this is if we were, say, raising z up to a 10th power or even higher. That definitely is going to save you considerable time and effort. Okay, well, let's end right here, and we'll be picking up with another video before long. We're going to talk about Duhamov's theorem, being able to find roots of complex numbers, and we're going to be using this idea that we just had right here, just extending it a little bit.